when things are coming about, let me tell you, when I was a graduate student, I worked on an interesting problem which is called shape-from shading. And shape-from shading involves the following problem. We know how light hits a matter and how the matter reflects back the light. You can simplify these equations with a very simple equation. I mean, assume that this is the surface, this is the light source direction. L would be the light source direction, and this would be the normal of the surface. I mean, this would be the normal of the surface here. So the most simple equation that describes how light interacts with matter, being pictured at a specific point, is basically the dot product between the normal of the surface and the light source. So what we basically see is the cosine of this angle up to something which is called albedo. And the question that I was occupied solving is how do you extract back the surface from this dot product? If you simplify, if you, for example, align the light source with the viewing direction, then you end up solving a very simple problem, and this is reconstructing the gradient of a function that is given to you by some value of x and y from its gradient magnitude. And this is obviously an ill-posed problem, but and at the time I was really happy that this is an ill-posed problem, because when you have an ill-posed problem, you can work on it for many years. This is how mathematicians like to work, and there is no worry that anyone would implement it eventually. And this lecture is coming to show you that I was so wrong, because you can actually solve this problem. I mean, you can reconstruct back the function from its gradient magnitude in 2 dimensions at least, and actually have really nice applications that are coming out of it. So this would be one of the topics in this talk. This talk would travel, it would be like tapas. This is the end of the week, and therefore I will show you many things that I've been involved with. But the main theme here should be that parameterization is really important. Picking up the right parameterization is in fact understanding. So when we are talking about learning, about computer vision and learning, we throw away the understanding because we assume that the parameterization is given to us, and this is something that I will try to communicate. So, first of all, about our playground. Those of you who heard me in Warwick, I apologize. Some of it would be just a repetition. So if we take an image and we process it, I mean, map it to itself, so let's to improve it. This is called image processing. If we try to understand what is going on inside the object, inside the image, I mean, extracting the geometry used to be called computer vision. Okay, so computer vision used to be thought of extracting the geometry out of a given image, and the inverse problem, taking some mathematical equations that describe the geometry and projecting it back into a nice-looking image, is called computer graphics. So again, computer graphics is the synthesis, computer vision is the analysis. This is where we play. And recently, there have been some mixtures between the two. You take off the domain in which the graphics operates, and you take objects from the virtual world and try to plug them into the real world. If you think about Pokemon Go, okay, this is it. This is called augmented reality. And if you do the opposite, I mean, taking things from the real world and embedding them into some virtual world, this is called virtual reality. You can find it if you put this Oculus Rift. Usually, this is what happens. Okay, so step by step into computer vision. The first problem in computer vision that people tried to tackle was the segmentation problem. I would like to look at this image and be able to say that there is a fence, and behind the fence there are some buildings, and there is a lighthouse at the back. And the assumption is that if I can, let's call it 2.5D, if I can segment it, if I can separate the objects, I have better understanding of what is going on inside the image. So just as a warm-up, let me show you how you can do something like that in a very simple manner by computing geodesics, by computing shortest paths. So assume that this is your problem. You have these starfish that you would like to segment from the background, and the game here is that you can do 2 scribbles. You can touch, put your finger like that and show that this is foreground, and do it again and show that this is background. And then the question is, how can you separate between foreground and background in the most efficient manner? So assume that you can compute something which is called probability map from these 2 scribbles, and now you compete between these 2 values of p in order to segment the object. So if you think about it, p would have, in the perfect world, p would have been 1 inside and 0 outside the object, And now you compete between these two scribbles in a continuous manner, where P, which is, for example, some function of the gray levels of the image, is the governing equation. Traditionally, Sapir and Bai, what they did is quantize the image so that pixels communicate with one another on a rectangular grid. If you do that, you're prone to have a problem. So parametrization is very important. What Anastasia Dubrovina did, she is now a postdoc at Stanford, is treating the image, the p-value of the image, as a graph, as a graph of its level sets. If you do that, you have the following representation of the image. So if this is the image of P, so the values here correspond to 1 background, say, and 5 foreground, and then you can translate it into a tree that looks like that, into a graph, and then what you need to do is is travel along this graph between source and destination and find the barycenter, call it Voronoi diagram of this graph, and thereby you get this spider here. And if you do it the traditional way of treating the image as connection, a square connection between pixels, what you get is something that looks like that. It's a little bit noisy. This is a movie that shows Anastasia after she segmented herself from the background. Here she blurs the background. In a moment, she would focus on the background and blur herself. And you can see that this method is actually working in practice. There is no way for special lenses, etc. There is a war story. When I came to the Technion, I got a grant that was enough to either buy a 3D sensor or hire 3 students. And what I decided to do is hire 3 students and tell one of them to build a sensor. This is how the sensor looked like. You can think about it as 2 eyes, a projector like that, and the camera. And this is what we get out of it. We licensed it to a company called Envision, and it was sold to Intel. In fact, the first, it's called RealSense. Intel RealSense is a scaled-down version of my lab's sensor. This is the local president of Israel presenting it in Las Vegas. This is the size of it comparing to Nevada currency. You can see the projector here, the camera, it's an IR camera here, and there was another camera there, and there is the brain behind it. And this is compared to our competitors at the time. Another interesting war story is that now, recently with iPhone X, they have scaled down the version of the original Kinect into a very similar form factor, 3.2 millimeters in width, and they put it in your telephone numbers, and in your cell phones, in your iPhone X, those of you that will buy them. And the reason that it was integrated there is esoteric. Apple wanted to use the OLED screen because the resolution is better, the intensity is better, the contrast is better, but through an OLED screen you cannot sense the fingerprints. Okay, it prevents it from being sensitive enough to read fingerprints. So what they had to do is somehow give up some equity of the screen at the top and plug their 3D sensor, and this is how you would enter your next generation phone, by looking at your face and using it as identity reader. So these are our competitors. When you optimize, when you do the design, you need to optimize not only for the accuracy, but also for the cost, and most of it would probably go to this guy, which promotes it. This is, he's talking about the sensor. But, okay, so believe me, it's funny, but there is no voice here, so we'll jump over it. So what did I want to show here? At the top, what you can see is the output of this sensor, which is really, really noisy because we have to scale it down and compress it into 3.2 millimeters. It's really, really noisy. But since we have an RGB image as additional layer, we can use the RGB in order to do shade from shading. If you do that, and this was done with Roy Orel, this guy, postdoc in Washington, Seattle. So if you do that, you can see that at the top, the image looks really noisy, and at the bottom, when you use the RGB in order to refine your noisy data, you can use shape from shading in order to actually look at the fingernail here and look at your line of life at the palm of the hand here. So again, I don't know if you can appreciate it, but this is shape from shading in action. Shape from shading can actually work. And now it's working on an NVIDIA processor that takes the data out of the RealSense sensor and improves it, and can actually create much better results. It looks better, and it's actually even better in PSNR sense, in L2 sense. Okay, we have 3D. What can we do with that? This is another project with Aaron Wetzler. He's now graduating and became a CTO of a company that is selling an app for segmenting things on the web. It's called Solo. I don't know if you've used it. What it did is, by learning, looking at the hand, at the 3D appearance of a hand, and identifying which finger is which, he was able to train. It's called a decision forest, a sequence of this. When you have features and you would like to do learning, what you usually do is called decision forests. Okay, so it's a simplification, if you would like, from neural networks. So he was able to identify which finger is which, but the clever thing about it is, how do you train it? I mean, how do you create a huge database in which each finger is identified? And what he did is put a sensor, electromagnetic sensor, at each and every finger, and use an antenna that creates some electromagnetic fields in the room, and therefore he knows which finger is which when recording the output of the camera. So this is how he was training that. These are 4 short clips that show, first of all, tracking of the hand, tracking of each and every finger, so he changes his poses and still able to identify which finger is which. And what you see over here, let me show it to you in a different movie. What you can see over here is a robot that we printed and assembled together. Here is the 3D sensing camera, and now Aaron is moving his finger, and the robot, besides doing this monotonic motion like that, also moves his fingers according to Aaron's fingers. And if I would have had more time, I would have shown you how he shakes his own hands. It's an interesting phenomenon. I mean, interesting feeling. Okay, what else can you do if you have a 3D sensor? If you have a 3D sensor, what we did is constructed inhalation masks for babies. So this guy, Israel Amirav, came to us and told us, look, I'm giving prescription for inhalation masks for babies, and the mothers are complaining because the babies would not take them, they wouldn't fit the face. This is just a scaled-down version of adult masks. What can you do? So we gave him the sensor. He scanned about 400 kids, small newborns, and then we classified them using Gromov-Hausdorff distance. I will not get to it in this lecture, but if you are interested, I'll be happy to talk about it. This is what we have been doing during the last century and a half, being able to approximate Gromov-Hausdorff distance between surfaces. Just to give you a glimpse about what is going on behind that, assume that the hand is manifold, and what you have is measurements of distances between all points to all points on this manifold. So you have D of the hand. This is a surface S between all points. Let's call it SI and SJ on the hand. And you would like to match a glove to this hand that would minimize the glove. I mean, now we have a glove. Let's call it DG. This would be for the glove, and you have GI and G. I mean, it would be different identities. So G1 and G2 between these points on the glove, and you're trying to optimize the mapping between all the points in S or all the point in G, so that this discrepancy measure would be minimized. We have done it. I mean, it looks like an NP hard problem because there is a combinatorial problem involved. But what we learned to do is, in fact, take it into the spectral domain. First of all, of the LBO of the surface, and then the spectral domain of this matrix, and work in that domain. And apparently, if you have low dimensionality, and surfaces are usually of low dimensions, you can do magic with this kind, optimizing this kind of measure. So we use this tool in order to classify all scanned faces into 3 groups, and then eventually Israel also wanted to have a hole for a pacifier for the baby, and this is how it looked like. And eventually this is how the final product looked like. It is now being sold, and we get letters from mothers, from parents that are really happy with this product. I mean, they said that it really saved their quiet, their level of living. So this is one thing that you can do with 3D sensor. Okay, I promised that I will talk about neural network. So before we get into artificial neural networks, let's talk a little bit about true neural networks, I mean gray matter. This is an experiment that was done in University of Southern California by Cao in Cao's lab. And this experiment is, what she did is she opened the skull of a macaque monkey and knew exactly where to pinpoint 200 electrodes in something which is called surface cells. And by recording the outputs of these surface cells, she was able to reconstruct back an image that was presented to the monkey. So again, the monkey sees these kind of images. She records 200 numbers, 200 features from the monkey's brain. And from these 200 numbers, she is able to reconstruct back these features, these images, in a very high accuracy, very high fidelity. And the question is, what can we do without opening skulls of monkeys? I mean, can we do better in some computational experiments? So remember these 200 numbers, because we'll come back to it in the next slide. And in the next slide, I would like to talk about what I think is a fundamental experiment in computer vision and computer graphics. And this is an experiment that was, a method that was built by Vetter and Blanks, two Swiss researchers. And what they did is they claimed the following. They claimed that the space of all possible geometries of faces can be captured by 200 numbers. And for that end, what they did is they scanned, I don't know, hundreds of people, 200 or 300 people. They manually, semi-manually, aligned all these surfaces so that each end of the nose would correspond along all possible realizations. Same goes for the end of the mouth, etc., etc. And then you have a vector of numbers for each and every face which have the same parameterization. They PCA, principal component analysis. We'll talk about it later, what it is exactly, but just think about factorizing these matrix. And took just the leading eigenvectors. And it's called a 3D morphable model. Okay. Now they get a new face, and what they're trying to do is fit a combination of these 200 vectors, so they have to control only 200 numbers, to a given face. So as you have seen before, what they do is they take manually a mask and they rotate it so that it will more or less fit the image, and then they just optimize these 200 numbers. And while doing so, they also optimize for the lighting directions, albedo, etc. And they get something that looks okay. But it was manual, it was tedious, and the question was how to optimize it. And more importantly, how to use a neural network. A neural network is, for our discussion, a box that would be able to interpolate data that we give it. So we give it x and y. A lot of this is called training data. And at the end of the day, we would like to give it new x, and I would like to get y, which is reasonable. And the question is how to construct a neural network that would be able to do something like that. And for that, what we did is we used their model in order to synthesize a lot of faces. So these are the faces that we are synthesizing. And we don't only synthesize faces, we also synthesize their geometries. So this is how it looks like. All these faces and all these geometries, which is something that we don't have otherwise. I mean, you don't have millions of faces and corresponding geometries, and they look as if they got stroke because we also play with the expressions. So this is what we do. So what do? We just choose within these 200 numbers some random combination of 200 numbers. From these 200 numbers, we extract the geometry and the photometry, and we now play with the pose. So you can just randomly play with the pose. You can play with the lighting direction as well as with the background. The background is just images that you grab from the web. And now you feed it to a network, after you train the network, and what you expect to have at the end of the day is something that looks like that. And this is a really good 3D reconstruction of this image. Now, I was cheating here a little bit. You cannot just take 200 numbers and get all the wrinkles and the fine details of the beard from DiCaprio. You need something beyond these 200 numbers, the 3DMM model. So what we did, the trick was the following. This was the first network that we used. We used the network to extract 200 numbers, these 200 numbers in the 3DMM space. Then we computed the result, which looked like that. It's a very smooth version of DiCaprio's face. And then what we did is resorted again to the shape from shading problem. So we know that this is the image. We know that this is how we were constructed. We can compute the residual, and we use the residual in order to compute the shape from shading missing data. So this is what we did over here. We just optimized for this equation, the discrepancy between this equation and what we see over here, and we got the fine details. This was fine. It gave us okay results. But then we asked the following question. Look, if we have a penalty here, we can in fact train a network that would take this axiomatic component and just use a network for that. And this is what we used here. So again, we get an image. From this image, we get 200 numbers in the 3D space. And then we translate these 200 numbers by hitting them with the eigenvectors to the geometry and the photometry. And then there is another network that is optimized for this equation that would provide to us the final surface. And again, this is how it looked before we call it finite. Eventually, this was presented in CMPPR. Eventually, what we did in ICCV is that, look, let's not restrict ourselves to be within this 200-dimensional space. Within the training, you can get rid of this difficulty by just training a network from I to Z. It's called pixel to pixel, and for that we use the UNet that can take wrinkles from one point and rotate them and translate them so that they would appear in another. And with that, we got really nice results. Let me show you the results in the middle of the model in the middle. This is how it looks like, and the model at the end is probably our best results right now, and I will show it at the end of this lecture. Okay, so how do we take it from here? Another experiment in learning, and this is reading facial expressions. So if we go more than 200 years back and look at the initial understanding of of the meaning of expressions, so the early steps in electrophysiology was actually by pushing electric currents into people's faces and see how they react. This is the original picture that you see over here. Now, the claim about expressions is that there are 7 universal or 8 universal ones. So whenever we are happy, we are smiling. So smile is a universal expression of happiness. The same goes for sadness, etc. These are the 7, including neutral, which is another one. And in fact, it was captured by Disney Studio Inside Out movie. So you can see it over here. These are 7 virtual creatures that are manipulating a teenager girl and telling her what to do according to how they decide to do something eventually. Now, this guy, Paul Ekman, was a psychologist that claimed that these 7 expressions are universal, and it took him about 7 or 8 years to realize that all these universal expressions are being controlled by 50 groups of muscles, which he called action units. So always when you are happy, you are stretching these parts of the face, and these are associated with a very specific group of muscles. And there is also a physiological explanation for that. And what he did is he built what he called facial action units. I don't want to spell the acronym, but and this is how they look like. So you have some which is upper lip raiser, etc., etc. This is chin raiser and corda depressor, etc. And he also trained experts in order to look at faces and be able to say what is going on in these with these action units. But the nice thing is that each and every expression can be realized by the same combination of action units. Okay, so smile will always be probably lip stretcher 820 plus upper lip raiser 810, etc. So this is a universal understanding of a psychologist. At the other end, now we don't want to open monkeys or anything to realize what is going on with expressions. At the other end, there have been neural networks that were trained to recognize faces, expressions on faces. How can we operate on them and see that what Ekman was claiming is true or false? This is what we did. So we looked at a trained network for facial expressions. We sliced, we bisected, we shaved off the last layer, which is the analysis, or let's call it the regression layer. And we looked at the neurons that were feeding this last layer. And my expectation was that among the 250 neurons, I mean silicon neurons that were activated, there should be some connection between that and the 50 action units of Ekman. So I gave it to Ram Brouwer, and they came back to me and told me, look, there are only 50 that are active. The rest of them are dead. I mean, you can just filter the network and just keep them, and they would give you the same result. And then we thought, okay, so there should be some linear relation between these 50 and the 50 action units. And then he comes back to me and tells me, look, these are exactly the action units. I mean, it's statistically exact in some sense. So what you realized is that you can, from training a network, obtain the same, and again, the training of the network is given an expression, say which expression it is from the 7 universal ones. And hit the layer before the last is actually the 50 action units that Ekman was looking for. Now he was able to train it on these expressions and then try to see how it operates in using micro expressions. So micro expressions are the small changes that happen when you, for example, tell a lie. This is how Ekman proved his claim. He showed that when Bill Clinton was asked, did you ever have sex with this woman? You could see he's saying, I never had sex with this woman, and then his eye goes up a little bit. I mean, and you really need to look at the video in order to understand something where it is happening. So what Ram did is train his network on these universal expressions, tested it on micro expressions, and got state-of-the-art result. It's not surprising because this is the first time that a network was applied to this problem, but still, I think it's an interesting story. And this is how, if you deconvolve the reactions of each and every neuron, this is how they would appear in the image, and indeed, they correspond to these action units of Ekman in one way or another. Okay, I still have half an hour, so let me talk about classical things in signal and image processing. Assume that you have a signal, okay? Now, this signal is just a function, and you would like to represent it in the most efficient way. And the question, what you have here is a set of other functions, and your function should be the projection onto this set of functions. And the question, if the only thing that you know is that your function is smooth, which basis functions would you choose to have? And this is a very fundamental question. For me as an engineer, I never was encountered with that, but this is a valid question. I mean, some of you, at least the mathematicians, should know the answer. Are you familiar with the answer? I mean, intuitively, which functions would you choose in order to represent a smooth function? Okay, let's ask the following.
Cosine transform.
Again?
Cosine transform.
Yeah, the Fourier. Okay, the cosine transform. And the reason is actually very simple if you think about it. What you have here is, I mean, the gradient, and it's a joint operator, is nothing but the Laplacian. The Laplacian is a circulant matrix. If you decompose it, you get the cosine transform, the Fourier, the harmonics. But it's more than that. We have been able to show that it is, besides being optimal, it is also unique. Okay, so if you don't know where you're going to stop your representation space, it should be unique. Now let's go to the other extreme. To the extreme in which you don't have this continuity assumption, I mean this smoothness assumption, but you have some, you know that your function belongs to relatively large set of given functions. So you have Fn. This is a classical, I mean, if you know how to solve this problem, then, and now again, the problem is the same. You would like to get any of these functions and being able to project it onto first k representative functions and be able to minimize this representation error. Again, this is a classical problem, and any of you who learned a little bit of data representation knows that this is nothing but the PCA, the principal component analysis, or the SVD of hitting these functions with themselves would give you the right functions. And again, you can prove that this is an optimal solution and unique one if you don't know where to stop by decay. Okay, so we have two regimes. One of them is all you know about your signal is smoothness. The other one is you know that your signal belongs to one of these, to a family of known signals, or to a statistical behavior. And the question is, what can you do with it? For example, the 3DMM use this model. Okay, so each vector here is the coordinates, the x, y, z coordinates of the face. And what we do is we just decompose it and use it as our three-dimensional morphological models. At the other end, Fourier is also very efficient. I mean, if all I know is the smoothness of the function, here I don't use it at all. Okay, I can have two coordinates, and the fact that they are nearby does not play any meaning here. In a moment, we will marry these two measures in order to give us something which I think is interesting. Okay, so now let's take another detour. Sorry for the jumps. But it is piecewise smooth, the lecture, I hope. I have here two curves in the plane, okay? Two one-dimensional curves in the plane, and here they are just differ from one another by translation and rotation, by scale, by equi-affine transformation, and by full affine transformation, where equi-affine is where the determinant that hits these coordinates is equal to 1. And the question again, how can we find parameterization that would allow us to compare and match these kind of objects? And the reason it is very important for image processing and computer vision is because if I'm looking from far away on a specific object, I can look at its contour. And projecting onto the left eye and the right eye, the transformation between these tiny contours could probably be affine. Okay, so affine is important, scale invariant is important. I would like to be able to match a small hand to a large hand and still say that this is the same hand. And the question is, how do we do that? So reminding you about elementary differential geometry, if we have a parameterized, oops, this is not what I wanted to do. So if I have a parameterized curve, the derivative according to the parameterization is the velocity or the tangent vector. And if I choose a very specific parameterization, this is constant traveling along the curve, what I get is the unit vector as the unit velocity. And the acceleration is nothing but the curvature vector. Okay, so the change of unit velocity would be the curvature, which is, not surprising, 1 over the radius of the oscillating circle at each and every point. So what do we do with that? These are the transformations that are of interest to us. Euclidean, affine, and equi-affine is where the area is preserved. Okay. And how do we analyze them? So if you would like to compare two curves that went through Euclidean transformation, what we can do is plot the curvature as a function of the Euclidean arc length and try to match these two signatures. Okay, so I do it for the left shark and the right shark. And now I take these two signatures. This is the curvature as a function of arc length. So as I travel along this contour, I compute the radius of the oscillating circle and I plot it as a graph. And when I'm trying to match these two graphs, I could say if these two curves in the plane are identical or not. Can we learn that? Can we learn differential geometry? So we used to think that geometry is understanding. The moment I understand, I know how to compare between two entities, I understand what is going on. And the answer is yes. And what we did with a student of mine, Gautam Pai, is the following trick. We trained the network, two networks, which is called Siamese network, by taking pieces of curves, of corresponding pieces of curves and different pieces of curves, and allowing the network, and we played with the parameterization by sampling these curves differently for each and every pieces of the curves. And we penalized the discrepancy between two different parts of the contour that we are matching and two identical parts. So if we travel along this relatively simple and nice contour and we plot the curvature, you get something that looks like this red plot here. But if we do that for the land network, what you get is something that looks much, much smoother because the numerical support of this network is looking at a larger portion of the curve. And you can use convolutional neural network in order to do that. And if you know the order of points, you can in fact introduce huge amount of noise and still preserve, this is the invariant of the network, and still preserve the identity that you obtain by looking at these bugs over here. Okay, these are the differential invariants that are completely washed out when you create huge amount of noise. There is something which is called integral invariance, which is a little bit more stable, but still you need to look at larger distances along the curve. So you can learn invariants. This is important. You can train a network to learn invariants. Why? Because you can synthesize them. And by synthesizing, you can actually train a network and push all our knowledge into this gray box. Something else which is really important before we lift into surfaces is the fact that when we take the curvature as a function of arc length and we try to match one curve to the other, there is this ambiguity of shift. I mean, you need to shift one data with respect to, I mean, you don't know where you start, okay? So you don't know where is the starting point. If you want to overcome this difficulty, there is a theorem by Cartan who said that what you need to do is take the curvature and its derivative by the arc length, and then you get a signature which would be invariant to any selection of point. So this would be the signature of the first shark, this would be the signature of the second shark, and by matching these two signatures, you can match between these entities. But, so this is a beautiful theoretical result. But there is a problem. The moment we go into third order derivatives here, second order derivative is the curvature, and then third order derivative, noise is amplified by an amount, especially when you go to more complicated transformations, noise is amplified, and we would like to avoid that. I'm not saying that I have an answer for that, but I'm just saying that there is a problem in this. So, how do we construct invariant arc length in order to understand, in order to train afterwards networks? In the Euclidean case, we know that length is preserved. So if length is preserved, you can start from wanting a parameterization such that the velocity would always be equal to 1. And at the end of the day, what we get is that the arc length is equal to velocity times the time. And this is nothing but Euclidean arc length, okay? Distance is equal to velocity multiplied by time. What happens when we look at more complicated scenarios, like the equi-affine? When area is preserved, you build your arc length in a different manner. The arc length is built such that the determinant, I mean, when you cross product the first and the secondary, let's call it the velocity and the acceleration, you would like it to be equal to 1. So this parallelogram should be equal to 1. And when you do that, at the end of the day, it turns out that the equi-affine arc length is nothing but the Euclidean arc length to the power of 1 over 3 times the Euclidean arc length. So this is a way of constructing equi-affine arc length. A more intuitive construction, I would say, is constructing arc length for scale invariance. So in scale invariance, if we're looking for an arc length that would be invariant to scaling, we know that ratio between length is preserved. So what we would like to have is parameterization, let's call it theta, so that the ratio between theta and the radius of the oscillating circle would always be equal to 1. Okay? I just invented something that would be invariant to scale. It turns out that the arc length is nothing but the change of the velocity angle. Okay, so if I'm traveling from here to here, integration over the change of this angle would be my invariant. And this is not so difficult to see, okay, because if I scaled up or down my curve, the change of angle would always remain the same. Okay, so it would be nothing but the curvature times the arc length. And if you think about it, this is the definition of the arc length. The curvature of the curvature. The curvature is the change of angle divided by Euclidean arc length. So I just packed something that you should, I mean, most of you should be familiar with in somewhat different manner. The question, and until now everything is known, and the question is how do we lift it, how do we take it to surfaces? This is just another example of the same. I mean, traveling from that point to that point, d theta is nothing but the change of the angle, and you can shrink or expand.
One question on the previous slide, it was curvature without absolute. Is this?
Well, yeah, think about it as an absolute value. If you'd like theta to be a positive arc length,
because otherwise it would cancel if you go on a certain.
Sure. If you can.
Or if you have a concavity, for example, it cancels.
Take it as an absolute value. You're right. Take it as an absolute value. Okay,
It's
so
the absolute curvature you're integrating simply.
yeah, you just integrate over
Which
the
is
absolute.
2 pi on all convex shapes, for example.
Yes. But as you travel along the curve, it should have different values that would correspond to corresponding points for scale down and scale up version of the curve.
Can you repeat this sentence?
Yeah, sure.
It was too fast.
Sure. If this is your two-scale version, so changing from that, you always accumulate, and here it would be negative. So from traveling from that point to that point, d theta should be identical to traveling from that point to that point. Okay, so although the radius of the curvature is different, etc., it should be the same number, which is the essence of scale invariance. What we would like to ask ourselves is, how do we take all this theory into surfaces? So for surfaces, equi-affine geometry is quite well established. It goes back to Blaschke and Buchin-Su and others. For scale invariance, it would not. I mean, they just left it open because geometry thought it was trivial, but it was just left out. So what do we do with surfaces? Let me just remind you about the Gaussian curvature. The Gaussian curvature is nothing but multiplication of the two principal curvatures at a surface. And a surface, this is a parameterized surface, can be defined, I mean, when you measure distances on a surface, it can be defined by something which is called the metric, which is nothing but the affine transformation of lifting from the parameterization space, the UV parameterization space, onto the surface itself. So this is nothing but SU, or S is X, Y, Z, dot product with the self. This is G11, G12, G21, G22. Okay, so this is, again, for mathematicians it should be trivial. For engineers, just think about it as affine transformation from the coordinate space to the surface itself. It would translate, it would allow you to measure distances on surfaces. And then the question is, how can we extend the idea of scale invariance into surfaces? And the answer is very simple. All you need to do is multiply these coefficients, these metric coefficients, by the Gaussian curvature. If you do that, you get a scale invariant pseudometric, okay? Because the Gaussian curvature could be equal to 0 at various points. So if you do that, you get a scale invariant pseudometrics. Now, something which is beautiful is because all we do is we scale the metric uniformly at each and every point. It would be a conformal mapping. I mean, it would be, in some sense, a very simple operation. And then if, for example, you want to define the Laplacian with respect to this modified metric, the Laplacian would involve only second-order derivatives. And for us engineers, it's very important. It's very important to always keep the number of derivatives that allow you to construct your spaces relatively low, because otherwise you amplify, you add more noise to the game. So, what do? We define a new arc length, which is nothing but the Gaussian curvature times the regular arc length. I mean, Gaussian times the coefficient of the arc length. And with that, we get a scale invariant metric. With the scale invariant metric, what we can do, okay, so we can now compare distances between objects. And if we use the regular metric, these bisections of the objects would not correspond. And if we use the right metric, then you can see that here we split this centaur with the manipulated head, and shoulders. Here the feature, the parts of the centaur would correspond. But more important, and obviously you can compute Hausdorff distance with this kind of measures. I mean, you can plug it into this kind of a model and find the correspondence between these objects. And here what we did is we scaled the head of this armadillo compared to that one, and we are still able to compare these objects, I mean to match these objects. But what is more important is the fact, let me see where I have is the fact that I can now take this operator, the Laplace-Beltrami operator, and when plugging the new metric, all I get is the second order derivatives of the curvature outside, and here everything is being kept as second order derivatives. So the order of derivatives are being kept, are being preserved as 2 when using the scale invariant metric. Again, it's from an engineering point of view, it's important. Now remember, I told you that smooth functions on surfaces, I mean on any manifold, are optimally represented by by taking the eigenfunctions of this operator. Okay, this is the extensions of the Fourier, and this is how it looks like if you don't. I mean, if you take the regular metric and you take the second, fourth, and fifth eigenfunctions, they would not correspond to one another. You can see the discrepancy between them. However, when you multiply by the Gaussian curvature, they would. I mean, you can now see here color correspond to values of the eigenfunctions of the Laplace-Beltrami operator, and now they would. So you can compute it, it's very efficient, and it's working really nice. I have 10 minutes, so I would like to tell you that indeed, you can take the Laplace-Beltrami eigenfunctions and prove that they are optimal in representing, in projecting smooth functions onto them, and they are unique. You can find that in a science paper by, in fact, this is the optimality. Uniqueness is in a different paper, and recently Brazil showed a very nice theorem for the continuous case, where you can prove optimality and uniqueness also not only for discrete, in the discrete setting, but also for continuous ones, with a very nice theorem over there. Okay, so we have the scale invariant metric, and we have the regular one. And I told you that you can do optimal representations of functions with respect to the metric. But then the question is which metric to select when I'm trying to represent this horse by 300 numbers. I mean, which should I go for the scale invariant one? Should I go for the regular one? I mean, should I go for something in between? This is something that I can compute the representation space for. And the answer is that there is no answer. I mean, it depends on your application. If you really care about the features, the small, the eyes and the head of this horse, then go for the scale invariant one. If you care about the global structure, then go for the regular one. But probably what you want to do is something in between. So this is how reconstruction of the head of the horse would look like with regular metric, with something in between the scale invariant and the regular one. And this is how it would look like with the scale invariant one. Just a comment. Jonathan Aflalo is the guy behind the 3D camera of the Samsung Note, the new, it's called S8 or something like that. And the reason is that he came to Samsung and they told him, look, you came from Kimmel's lab, so you should do 3D. So this is what he did in his research, but now he's doing 3D cameras. Okay, back to which basis to use. So if you really like the features, probably you should use this one. If you want to be something in the middle, probably you should use this one in order to construct your basis. Otherwise, you could use the smooth version. And this is how the original horse used to look. Okay, so I think that I have enough time to marry the two, and this will probably be the conclusion here. So, assume that you have these observations, now I call them X, and I'm trying to find the PCA, the principal component analysis, which is a basis that should be orthogonal at one end, and at the other end, minimize this representation error. This is the PCA idea. At the other end, if I'd like to extract the Fourier, the cosines, the harmonics, what I would like to minimize at the end of the day is the Dirichlet energy. And the question is, why can't we combine them? I mean, in surfaces, we know how each point is related to the other. I don't want to just relate to all the set of the points as unrelated. I would like to relate between them. Can we actually do something better? And the answer is yes. We can take the Laplace-Beltrami operator, which is the result of the Dirichlet energy, and combine it with the measure of the PCA. And when you do that, you get a new operator. In fact, you can prove that this operator will give you an optimal and unique basis for that kind of metric that you have now constructed. So let's do the following experiment. I have these two observations of the dog, x1 and x2. And from these two new observations, what I would like to do is reconstruct this dog. Now, this dog is different from these observations because he tilts his head to the right. And the first eigenvectors that I extract from these dogs would not include this rotation of the head. So if I'm trying to extract back the dog using just the PCA part, this is what I would get. I would get really good fidelity of all the fine details, but he would not be able to reconstruct back his head to the left here. If I'm using just the Fourier, just the smooth version of the dog, then the rotation would be captured, but the details would not. And if I marry them, if I take both of them and use both of them for the reconstruction, this is what I would get. And this is how it looks like. This is the training. These are the tests, and this is how the LBO result, the Fourier would look like. And this is how the PCA would look like. So we can see that when the dog is really curved, what you get is a mess. However, when you try, and again, 300 numbers, do the reconstruction. But when you do the regularized PCA, I mean regularized with the smoothness assumption that each point is actually related to its neighbors, what you get is really good reconstruction of the dog. So my claim here, my take-home message here, is that if you do PCA in computer vision and graphics, also add the regularity of the neighborhoods between points that is being captured by the Laplace Beltrami operator. It would allow you to use the same order, the same number of surfaces of eigenfunctions and get much better results. And this is how the new 3D reconstruction looks like. You can see the fine details here, and again, there have been many things that I tried to cover here, and usually I lose the main thing. But I think that the most important part is a statement that was made by Picasso, who said that computers are stupid; they can only provide you answers. And the question is how to ask the right questions. I mean, when we are now entering this problematic era of deep learning, and you can completely eliminate the word understanding from image understanding, you should still ask interesting questions, and with the right training, probably get interesting answers. Okay, I end here.
Yeah, we should welcome questions and comments.
I mean, I'll be here until Tuesday, Wednesday. Yep.
So, in reality, I mean, when engineering a computer vision system, let's think about when we might want invariants to some class of transformations, right? So, rarely do objects in the world actually Euclideanly scale themselves. What's more likely to happen is a camera changes its focal length and we move backwards and forwards near an object. And what happens is that the set of transformations we observe is a subset of, let's say, the set of homographies. But it doesn't happen to be one of the subsets we've identified in mathematics. It doesn't happen to be one of the subgroups of the set. It's just a set.
This is true.
So and then a natural extension is, well, actually I don't want to just do a constrained optimization inside the set or outside. I want to optimize on some probability density over all the transformations.
I also completely agree. So my claim is that if you know the subset that you are operating in, you can either, take pictures of the real world and train a network, but you don't always have this luxury. In some cases, in most cases you don't. So synthesize them. Use all the axiomatic methods that we have learned how to do during the last 50 years, even before I was born. But use all these nice tools that we have in order to synthesize them. Train your interpolation methodology. Learn the statistics of your space, and then use it. So again, everybody now loves to look at real images because real images are real. But you don't, for example, when you're trying to do 3D reconstruction, you don't have 3D geometries of faces. So what can you do? And what you should do is do as much as you can by training, and this is the smooth part, and then use the axiomatic knowledge in order to put the last nail to this problem. So I don't have an answer that how can you analyze subsets or subgroups or whatever. This is from a mathematical point of view, it's a huge problem. But training would actually capture all these subtleties and actually would compensate for things that we don't really care about. And this is how do you quantize? Usually you look at an image and the image is more than smoothing. It's also realization onto some pixel set. So if you don't want to deal with that, just train it. And then the question is, how should we define a new sensing devices that would be optimal? And then we'll have to go back to the axiomatic method and try to analyze it again.
Yes, because we all feel there's value in understanding about concepts like curvature.
Yeah.
You know, that we should be able to make use of that.
But something more than that. For example, if you would train a system to do curve identification, what you would do is lift it into some many-dimensional feature space. What I'm telling you is that, look, looking at Cartan's theorem, you can limit yourselves to a curve in the plane. This should be enough. This should be sufficient. So lift it to a third dimension. That's it. But this is a bound on what you need. And if your network is lifting it into a very high dimensional space, then something is wrong there. So we can learn from networks. It's not. I mean.
Any other comments or questions? So from one part you're talking, it seems the 3D human face is only about 200 some dimensions.
It's actually the 200 numbers that refer also to the photometry and the isometry and the geometry. So the geometry is only 100 numbers. So, but this is the smooth version of the face.
So that's good news, right?
Yeah, we can lose a lot of neurons in our gray matter and still be able to recognize that. I mean, to capture faces, probably. But I doubt it if the brain is doing PCA. I mean.
Yeah. Okay.
So run to the from image to this surface, you select key points. Do you use the segmentation techniques at all?
You're talking about the Tsao experiment?
Well, for the last picture you showed.
Oh, here?
Yeah. What do you yeah, this one.
So over here, what we do is first of all we iterate on the pose. No segmentation at all. You just take the image from the net and you throw it to the network, and then the network just try to fit a model. You iterate over the pose, and then the network outputs this Z, and then you refine this. So there are some stages over there. Then you try to fit this Z onto a template, and then the template is being processed so that you add defined details using this kind of axiomatic part. So, and then we take in the last version, we take the network from end to end and optimize for everything from end to end. So it's a closed box. You take an image, and the output would be the 3D geometry of the face inside the image.
How do you prepare the training data?
3DMM. 3DMM is the training data. So okay, this is a good question. The question is, how do we construct our own 3DMM, because Veteran Blast would not provide us. So what we did is we took a database of facial expressions with 3D, and there you have the face and the geometry. There are about 500 faces like that, and from that we created our own 3D MM model. As far as I remember, it was people from Turkey. So if we are trying to then fit it to a baby from Congo, there were problems. So if you are trying to do it from scratch, what you need to do is sample as many ethnicities and realizations of faces, and now we're actually doing that. And there are groups in England that are actually trying to sell this kind of data from academia and others that have this huge amount of faces that they are trying to sell as a 3DMM model. So if they would have given us the original 3D from which they constructed the data, I would be really happy to buy that. But since they are just selling us the PCA vectors, we don't like it.
Do you have any ideas to open the box and see what's inside?
The box here.
The neural network box, yes. I guess you're interested in what's happening.
Yes, we are. At the time being, we haven't done that because it was too complicated as is. And my assumption is that among each and every feature you would find, about the eye and the nose, you would find something like like eigen eyes or something like that. I mean, you would find the structures inside, and the network is just picking up the right combination. So it should be something like a police work, I would expect. But I cannot say anything about what is going on behind the hood for the face reconstruction.
Any other question or comments? Okay.
So happy weekend.
Yeah, yeah.